What if everything we thought we knew about how planets behave was turned upside down, literally? Picture a world where the rules of gravity seem to rewrite themselves, where a planet doesn't just orbit its star, it does so in reverse, spinning backward against the cosmic grain. And as if that weren't strange enough, this rebellious world is wrapped in a swirling ring of dust, a silent witness to its defiance. This isn't the plot of a sci-fi blockbuster. It's real, it's out there, and it's forcing scientists to rethink the very foundations of planetary science. For centuries, we've mapped the heavens with the assumption that planets move in orderly, predictable paths, all dancing in the same direction around their stars, like runners on a track. But then came the discovery of an exoplanet that breaks all the rules, a world that moves backward against the flow, dragging its dusty ring along like a cosmic rebel. How does such a thing even exist? What forces could twist a planet's orbit into such a bizarre configuration? The answers lie in a mix of violent collisions, gravitational tug-of-wars, and maybe even encounters with passing stars, each possibility more thrilling than the last. This is the story of one of space's greatest enigmas, a dust-shrouded planet that shouldn't be, yet defiantly is. It's a puzzle that stretches our imagination and challenges our textbooks, a reminder that the universe still holds secrets we've barely begun to uncover. So buckle up, we're about to dive deep into the mystery of this backward world, where every clue leads to more questions, and where the very fabric of planetary science gets turned inside out. By the end, you'll see the cosmos in a whole new light, wondering what other impossibilities might be waiting among the stars. To understand this cosmic rebel, we first have to grasp what retrograde motion really means. In most planetary systems, planets form from a spinning disk of gas and dust, inheriting their star's rotation like children following a parent's lead. They all move in the same direction, clockwise or counterclockwise, locked in a harmonious celestial ballet, but a retrograde orbit flips the script entirely. Imagine a dancer suddenly spinning the wrong way while the rest of the troupe moves in unison. That's what's happening here, a planet stubbornly orbiting backward against the flow of its star's spin. What could cause such a dramatic defiance of the norm? Scientists have pieced together a few jaw-dropping possibilities. One leading theory involves gravitational chaos. Perhaps this planet was violently yanked off course by a close encounter with another massive object, like a rogue planet or a passing star. Picture a game of cosmic pinball where gravitational forces slingshot worlds into bizarre new paths. Another idea suggests the planet didn't form in this system at all. It might have been captured from elsewhere, dragged into orbit like a celestial hitchhiker with its own strange history. But here's where it gets even weirder, that mysterious dust ring encircling the planet. Normally, debris disks align with a planet's orbit, like rings around Saturn following its graceful path. Yet this one seems to cling to its backward-moving host, as if defying gravity itself. Some researchers think the dust could be remnants of a colossal collision, shattered fragments still trailing the planet's rebellious journey. Others speculate the ring might be actively shaped by unseen forces, maybe hidden moons or magnetic fields tugging at the particles, sculpting them into this surreal configuration. Every clue deepens the mystery. Retrograde motion isn't just a quirk, it's a window into the turbulent, unpredictable side of the universe. Most planets follow the rules, but this one, it's rewriting them, and as we untangle its secrets, we're forced to ask, if a planet can move backward, what other cosmic surprises are waiting to be discovered? The hunt for this cosmic rule breaker began not with a dramatic fanfare, but with the quiet persistence of astronomers scanning the skies for anomalies. Powerful telescopes like the European Southern Observatory's Very Large Telescope and NAS, a Kepler Space Observatory, played starring roles. Their lenses trained on distant stars for the tiniest flickers of light, the telltale dimming that betrays a planet crossing in front of its sun. But this time, something was off. The planet's transit data didn't match the expected patterns. Instead of a clean, predictable dip in starlight, the readings hinted at an orbit tilted at an extreme angle, almost as if the planet were moving sideways compared to its star's rotation. Then came the clincher, spectroscopy. By splitting the star's light into a rainbow of wavelengths, scientists could detect the subtle wobble induced by the planet's gravity. Normally, this Doppler shift reveals a star gently swaying in sync with its orbiting worlds. But here, the data told a different story, a star and planet seemingly at odds, their motions locked in a gravitational tug of war. The planet wasn't just misaligned, it was marching to the beat of its own drum, tracing a path backward around its host. This wasn't merely a detection, it was a revolution in disguise. For decades, planetary formation models had painted a tidy picture, swirling disks of gas and dust collapsing into orderly systems, with planets neatly aligned like pearls on a string. But this rogue world shattered that simplicity. Its very existence forced astronomers to confront a universe far messier and more dynamic than textbooks suggested. Suddenly, the calm, predictable cosmos seemed capable of planetary mutiny, a place where gravitational encounters could flip orbits like a coin toss. The discovery tools themselves became part of the story. Transit photometry, the technique that spots planets by their shadow, usually excels at finding typical worlds, not rebels. Yet here it was, catching the subtle signature of a misfit. Spectroscopy, often used to measure a planet's composition, instead revealed its orbital defiance. These instruments, designed for one purpose, stumbled upon something far stranger, proving that sometimes the most groundbreaking discoveries happen when scientists least expect them. What makes this find even more extraordinary is how it redefined the search for exoplanets. Before, astronomers focused on finding Earth-like worlds in habitable zones. Now they're just as intrigued by the oddballs, the planets that break the mold. This backward-orbiting enigma didn't just expand our catalog of exoplanets, it expanded our imagination, reminding us that the universe thrives on surprises. And as telescopes grow more advanced, who knows what other cosmic rebels are waiting to be found, each one ready to append another piece of what we thought we knew. That dust ring wrapped around this backward world isn't just a cosmic accessory, it's a smoking gun, a silent record of violence written in shattered rock and ice. Imagine a band of debris, not neatly aligned like Saturn's pristine rings, but tilted, warped, and moving in the wrong direction, as if the universe hit rewind. This isn't just a ring, it's a crime scene, and the clues hidden within its swirling particles could rewrite everything we know about how planetary systems evolve. So how does a ring like this even form around a planet that orbits backward? One leading theory points to chaos specifically, a catastrophic collision. Picture this, a massive moon, once peacefully orbiting the planet, gets caught in a gravitational crossfire. Perhaps another object, a rogue planet, a wandering asteroid slammed into it, shattering it into countless fragments. The debris, instead of scattering into space, gets trapped by the planet's gravity, forming a ring that inherits its host's rebellious motion. It's like a car crash in slow motion, where the wreckage keeps circling the scene, defying the flow of traffic. But there's another, even wilder possibility. The ring might not belong to the planet at all. Some scientists suggest it could be the remnants of a disrupted protoplanetary disk, the very material that birthed the system. Normally, these disks disappear as planets form, but in this case, gravitational turmoil might have ripped a chunk of it away, leaving it stranded in orbit around the rogue planet. Think of it like a piece of the original construction site, still clinging to a building that's since been knocked off its foundation. The ring's composition adds another layer of intrigue. Unlike Saturn's icy rings, this one might be rich in silicates and metals, stuff you'd expect from pulverized rock rather than frozen gas. Spectroscopic observations could reveal whether it's made of ancient planetary crust, the guts of a demolished moon, or even interstellar material snagged during the planet's chaotic journey. Every grain of dust is a timestamp, a clue to the cataclysmic events that shaped this system. And then there's the ring's structure. It's not uniform, it's lumpy, with gaps and clumps that hint at unseen forces at work. Could hidden shepherd moons, tiny and elusive, be sculpting the debris, or are magnetic fields generated by the planet's core, pushing and pulling the dust into strange formations? Even the ring's tilt is a puzzle. Rings usually flatten into a neat plane over time, but this one stubbornly refuses, its angle a defiant middle finger to the laws of physics as we know them. What's clear is that this dust ring isn't just an oddity, it's a testament to the universe's capacity for rebellion. It forces us to ask, if a planet can drag a ring of debris backward through space, what other gravitational gymnastics are possible? Every anomaly we find chips away at the neat, orderly models we've built, replacing them with something far more thrilling, a cosmos where chaos and creativity reign. And as we peer deeper into the mysteries of this twisted system, one thing becomes certain: the universe loves a good plot twist. The dust ring encircling this backward-moving planet is more than just a cosmic oddity. It's a forensic puzzle, a celestial cold case waiting to be cracked. How did this twisted loop of debris come to exist, defying the natural order of its system? Scientists have pieced together two spine-tingling theories, each more dramatic than the last. The first theory reads like a blockbuster disaster movie, a cataclysmic collision. Imagine two massive planetary bodies, perhaps a moon and a rogue asteroid, slamming into each other with unimaginable force. The impact wouldn't just shatter them, it would vaporize rock, melt metal, and hurl debris in every direction. Most of that wreckage would escape into space, but some fragments could be captured by the planet's gravity, trapped in orbit like cosmic shrapnel. Here's the twist: if the collision happened at just the right angle, the debris might inherit the planet's backward motion, spinning against the system's natural flow like a car skidding on ice. But there's another, even wilder possibility: gravitational sabotage. Picture a passing star or a rogue planet, an interstellar drifter, wandering too close to this system. Its gravity could yank the dust ring like a puppet master pulling strings, warping its path until it's spinning backward. This wouldn't be a quick process. It'd be a slow-motion heist, with the intruder's gravity stealing the ring's original motion over millions of years. Some astronomers even speculate the intruder might have flipped the planet's orbit first, leaving the dust ring as collateral damage in its gravitational crime spree. The evidence for each theory is tantalizing but incomplete. Collisions should leave behind chemical fingerprints, unusual ratios of metals or silicates in the dust that telescopes might detect. Gravitational theft, on the other hand, could explain why the ring's tilt doesn't match the planet's angle perfectly, as if it's still recovering from the cosmic mugging. Yet mysteries linger. Why hasn't the dust ring dissipated over time? What keeps its particles from clumping back into moons? Every answer leads to new questions, proving that in the cosmos, even the most violent events can leave behind the most delicate clues. One thing's certain: whether it was a smash-up or a gravitational hijacking, this dust ring is a testament to chaos. It's a reminder that planetary systems aren't static museums. They're demolition derbies, construction sites, and crime scenes all at once. And as we study this twisted loop of debris, we're not just solving a puzzle. We're learning how the universe bends, breaks, and sometimes rewrites its own rules. Gravity in this backward orbiting system isn't just a force, it's a full-blown cosmic wrestling match, with the star, planet, and dust ring locked in a perpetual struggle for dominance. Picture this: the star's immense gravity tries to pull everything into orderly alignment, like a parent attempting to straighten a rebellious child's path. Meanwhile, the planet resists with every ounce of its mass, dragging its dusty entourage along on its backward march. And caught in the middle, that mysterious ring of debris, somehow maintaining its shape despite being tugged in opposing directions. It's a celestial tightrope act where even the slightest shift could send the entire system spiraling into chaos. Astrophysicists have turned to supercomputer simulations to unravel this gravitational knot, feeding in variables like mass, velocity, and orbital tilt to watch the drama unfold in digital space. These virtual labs reveal something astonishing: the system shouldn't be stable. Conventional models predict the dust ring should have disintegrated eons ago, scattered by the star's pull or swallowed by the planet's gravity. Yet there it persists, a defiant loop of debris that refuses to play by the rules. The simulations suggest hidden mechanisms at work, perhaps resonant forces, where gravitational pushes and pulls accidentally sync up in just the right way to create pockets of stability. Think of it like a playground seesaw finding perfect balance despite uneven weights on either side. The implications ripple far beyond this one rogue world. If such gravitational anomalies can exist, then our entire understanding of planetary system evolution might need rewriting. For decades, astronomers assumed most systems settled into predictable, harmonious arrangements over time. But this chaotic dance proves some worlds never fall in line. They carve their own paths, bending the laws of physics to their will. It's as if we've been studying classical music while the universe has been blasting heavy metal all along. What's even more mind-bending is how these forces might influence other cosmic phenomena. Could retrograde orbits explain oddities like hot Jupiter's gas giants parked bizarrely close to their stars? Might they play a role in planetary migration, where worlds shuffle positions like cards in a deck? Each question pulls us deeper into a labyrinth of gravitational mysteries, where every answer reveals three new puzzles. And let's not forget the dust ring's role in this saga. Normally, rings are ephemeral features, destined to fade as particles clump into moons or spiral into their host planet. But this one defies the odds, its particles seemingly suspended in a gravitational sweet spot. Some researchers speculate magnetic fields or electrostatic forces might be at play, creating invisible scaffolding that holds the ring together. Others wonder if the ring is younger than we think, a recent addition from a moon shattered by tidal forces, its debris not yet had time to disperse. One thing's certain: this system is a masterclass in cosmic resilience. Against all odds, its contradictory forces have reached an uneasy truce, a testament to the universe's knack for finding balance in the most unlikely places. As telescopes grow sharper and simulations more advanced, we're not just studying a planetary oddity, we're glimpsing the untamed heart of gravity itself, where chaos and order wage an endless, breathtaking war. Planetary migration usually follows a predictable script, worlds drifting inward or outward like slow-moving commuters in a cosmic transit system. But this exoplanet didn't just change lanes, it flipped direction entirely, like a driver suddenly throwing their car into reverse on the highway. So how does a planet pull off such a reckless U-turn? The answer lies in the chaotic dance of gravity, where a single misstep can send a world spiraling off course in ways that defy intuition. One leading suspect in this orbital heist is the protoplanetary disk, the swirling cloud of gas and dust that birthed the system. Normally, these disks act like celestial traffic cops, gently shepherding planets into orderly orbits. But if the disk itself was warped or lopsided, perhaps by the gravitational tug of a passing star, it could have yanked the planet onto a wild new path. Imagine a roller coaster derailing mid-ride, its cars whipped sideways by a broken track. That's the kind of gravitational turbulence we're talking about, a system so unstable it could fling a planet backward like a slingshot. Then there's the possibility of planetary pinball. Picture this, a close encounter with a massive sibling planet, their gravitational fields colliding like bumper cars. The larger world might have slingshotted its smaller neighbor into a retrograde orbit, stealing its forward momentum and leaving it to drift backward. It's a cosmic version of a pool cue striking a ball, except here, the ball is an entire planet and the table is the void of space. But here's the real kicker. This backward journey might explain why the dust ring hasn't disintegrated. Most migrating planets lose their debris trails as they plow through their star's gravitational field. Yet this one's ring clings on, possibly because its retrograde motion creates a gravitational eddy, a quiet pocket where dust particles can swirl undisturbed. Think of it like walking against the wind. Sometimes going backward creates a sheltered space where things can linger. The implications are staggering. If planets can be hurled into reverse, then migration isn't just a gentle drift, it's a violent, unpredictable process that can twist systems into bizarre configurations. Suddenly, the universe feels less like a clockwork mechanism and more like a demolition derby, where gravity's rules are written in pencil, not stone. And as we uncover more of these orbital rebels, we're left wondering, how many other worlds are out there moving to the beat of their own chaotic rhythm? Most exoplanets we've discovered move in harmony with their stars, like well-behaved dancers following the same choreography. Hot Jupiters blaze close to their suns, super-Earths hug their orbits snugly, all marching in predictable prograde motion. Then there's this maverick, spinning backward like a lone breakdancer in a ballet troupe. Its defiance isn't just a quirk, it's a cosmic anomaly that forces us to reconsider what normal even means in the grand scheme of planetary systems. Take hot Jupiters, those gas giants that hug their stars closer than Mercury orbits our Sun. While they're extreme, they still follow the rules, orbiting in the same direction as their star's rotation. Even the infamous HD 80606b, a planet with seasons so violent they'd vaporize steel, plays by the book orbitally. Then there's super-Earths like JJ1214b, blanketed in crushing atmospheres, yet still moving predictably forward. Against this orderly backdrop, our retrograde rebel stands out like a skater grinding up a down escalator. The dust ring adds another layer of uniqueness. Saturn's iconic rings, they're pristine, icy, and perfectly aligned with the planet's equator. Even the bizarrely tilted rings of Uranus look orderly compared to this mess. Here, the dust behaves like smoke caught in a whirlwind, swirling against the natural flow of the system. Some debris disks around young stars show warps or gaps, but none exhibit this level of gravitational defiance, a ring that not only orbits backward but does so while clinging to a planet that itself defies convention. What truly sets this system apart is its storytelling power. Other exoplanets reveal extremes of temperature or size, but this one whispers of cosmic bar, fights collisions, captures, and gravitational hijackings that left permanent scars. While most worlds show us how planets form, this one shows us how they break, and in that brokenness lies its greatest value, proof that the universe doesn't just build. It rebels. Now consider the implications. If one planet can flip its orbit, how many others might be hiding similar secrets? Current detection methods favor orderly worlds, the low-hanging fruit of the cosmos. But as telescopes grow more sensitive, we might uncover entire populations of these backward wanderers, each with its own tale of gravitational mutiny. The very fact that this outlier exists suggests our exoplanet playbook is missing whole chapters. And if dust rings can survive such chaos, what other structures might lurk in the gravitational shadows, waiting to rewrite the rules? Saturn's dazzling rings might be the poster child for planetary bling, but this rogue exoplanet's dusty halo is rewriting the rulebook. Where Saturn's iconic loops shine with pristine water ice, reflecting sunlight like cosmic mirrors, this backward world's ring could be forged from something far darker: pulverized rock, shattered metal, even the scorched remnants of ancient collisions. The difference isn't just cosmetic. While Saturn's rings glide smoothly along its equator like a hula hoop, this one clings at odd angles, its particles locked in a gravitational tug of war between the planet's backward motion and its star's relentless pull. The composition alone tells a story of violence. Silicate particles, the stuff of smashed asteroids and vaporized crusts, would scatter light differently than ice, absorbing rather than reflecting it. Imagine comparing a snowbank to a pile of soot. One glows, the other swallows light whole. Then there's the possibility of metallic debris, which could mean the remnants of a planetary core torn apart by gravitational forces. Spectroscopy might reveal telltale signatures of iron or nickel, the cosmic equivalent of finding bullet fragments at a crime scene. Structure is where things get truly bizarre. Saturn's rings divide neatly into bands separated by shepherd moons, their edges sharp as knife cuts. This exoplanet's ring, it's a turbulent mess with clumps and voids that suggest ongoing chaos. Some sections might be denser where debris accumulates in gravitational eddies, while others stretch thin where particles get slung outward. Unlike Saturn's flat, orderly disks, this ring could twist like a warped vinyl record, its plane tilted by the planet's rebellious orbit. Formation is the ultimate mystery. Saturn's rings likely formed from a shattered moon or leftover disk material, settling into alignment over eons. But this ring exists despite its environment, a feat like keeping a sandcastle intact during a hurricane. One theory suggests it's actively replenished by ongoing collisions in the planet's vicinity, a perpetual demolition derby feeding fresh debris into the loop. Another posits that retrograde motion creates stability where there should be none, trapping particles in pockets of gravitational calm. What makes this ring extraordinary isn't just its defiance, it's what it reveals about the universe's capacity for chaos. Saturn shows us beauty in order. This tangled halo shows us beauty in rebellion. As telescopes peer deeper, we might find these twisted rings aren't flukes but markers of hidden cosmic dramas, each one a scar left by the universe's most violent dances. Spectroscopy turns starlight into a cosmic detective, revealing secrets hidden within that backward planet's dust ring. When light from the host star passes through the swirling debris, it doesn't just dim, it changes. Molecules and minerals in the ring absorb specific wavelengths, leaving behind dark lines in the spectrum like fingerprints at a crime scene. These spectral signatures are the ring's chemical diary, and astronomers are flipping through its pages to piece together a story of violence and chaos. Take silicate grains, for example. If the spectrum shows absorption bands around 10 and 20 micrometers, it's a dead giveaway for pulverized rock, the shattered remains of asteroids or moons caught in a catastrophic collision. Spot a spike at 4.6 micrometers, that's carbon monoxide gas, possibly from ice-rich bodies vaporized on impact. And if the data reveals unusual metallic traces like iron or nickel, it could mean the ring contains fragments of a planetary core torn apart by gravitational forces. Every element leaves its mark, turning light into a timeline of destruction. But spectroscopy doesn't just reveal what the ring is made of, it tells us how it behaves. Doppler shifts in the spectral lines can expose the dust's motion, showing whether particles swirl uniformly or spiral in chaotic eddies. Some lines might even appear smeared, hinting at extreme temperatures where material is constantly vaporizing and recondensing, like a cosmic version of steam rising off asphalt. And if certain molecules appear only on one side of the ring, it could mean ongoing bombardment from micrometeorites, freshening the debris like snowfall on a dirty windshield. The most tantalizing clues come from what's missing. A surprising lack of water ice signatures would rule out origins like Saturn's rings, which are frozen relics of the solar system's birth. Instead, a dry, rocky composition points to a hotter, more violent past, perhaps a moon ripped apart by tidal forces as the planet migrated backward. Alternatively, detected organic compounds might suggest the ring harbors probiotic molecules, forged in collisions and preserved in the cold void. This isn't just about decoding a single ring. These spectral fingerprints are teaching us how planetary systems rewrite their own histories. When we compare them to debris disks around other stars, patterns emerge. Some show similar silicate signatures, hinting at shared chaos. Others lack metals entirely, suggesting gentler origins. Each spectrum is a puzzle piece in understanding how often planets rebel, how often rings form from catastrophe, and how often the universe defies our expectations. The light passing through that dust isn't just radiation, it's a message from the cosmos, written in atoms and motion, waiting to be read. Rings shouldn't last in chaos. Normally, their delicate structures, think of Saturn's iconic loops, sculpted by gravity and shepherded by tiny moons into perfect harmony. But this dusty halo around a backward spinning planet defies all expectations, clinging to existence like a spiderweb in a hurricane. So how does it survive? The answer might lie in unseen guardians or hidden forces working behind the scenes, bending the rules of physics to keep this cosmic oddity intact. One possibility involves shepherd moons, small, stealthy satellites hiding within the ring's debris. Just as Saturn's moons Pandora and Prometheus herd its rings into sharp edges, these unseen sentinels could use their gravity to corral stray particles, preventing the dust from dispersing into space. But here's the twist: in a retrograde system, their job would be far harder. Instead of gently guiding particles, they'd be fighting against the planet's backward motion, like lifeguards swimming upstream to rescue someone caught in a riptide. Their gravitational nudges would need to be perfectly timed, creating pockets of stability where chaos should reign. Then there's magnetism. If the planet has a strong magnetic field, perhaps fueled by a molten metal core, it could interact with charged dust particles, effectively creating an invisible scaffold. Picture a child's magnet picking up iron filings. The field organizes the particles into patterns without touching them. In this case, the planet's magnetism might repel or trap certain debris, sculpting the ring into a shape that defies its violent surroundings. It's a delicate balance: too weak and the field wouldn't matter, too strong and it might shred the ring entirely. But the wildest theory: the ring isn't stable at all. It might be a temporary illusion, a structure constantly on the brink of collapse but somehow replenished. Imagine a fountain where water appears frozen in midair, except instead of water, it's shattered rock and metal, fed by an ongoing bombardment of micrometeorites or the slow disintegration of a dying moon. Every time particles drift away, new debris takes their place, creating the illusion of permanence in a system that's anything but. What's clear is that this ring isn't just surviving, it's thriving against the odds. Its persistence hints at forces we're only beginning to understand, a reminder that the universe has more tricks up its sleeve than our textbooks can contain. Whether through hidden moons, magnetic sleight of hand, or a cosmic conveyor belt of debris, this ring challenges us to rethink what's possible. And as we unravel its secrets, we're not just solving a puzzle, we're rewriting the playbook on how cosmic structures endure in the most unlikely places. Shepherd moons might sound like something from mythology, but in the cosmic scheme of things, they're more like invisible architects, tiny worlds with enough gravity to sculpt entire rings out of chaos. Saturn's moons Pan and Daphnes are perfect examples, carving gaps in the rings so precise they look machine-made. Now, imagine that same delicate craftsmanship happening around a planet moving backward, its dust rings swirling in defiance. If unseen moons are indeed shaping this exoplanet's twisted debris field, they'd be working against the odds, fighting not just gravity, but an entire system hell-bent on disorder. The evidence is tantalizingly indirect. Gaps or clumps in the ring's structure could betray the presence of these hidden shepherds. Just as a pebble dropped in a stream creates ripples, a moon's gravity would nudge nearby particles into neat edges or strange kinks. Some astronomers have even spotted what they call propeller features, tiny wing-shaped disturbances in the dust, likely carved by moonlets too small to see directly. These cosmic breadcrumbs hint at unseen forces at play, like shadows of puppeteers moving behind a curtain. But detecting these moons is like trying to spot a firefly in a foggy stadium. The planet's glare, the dust's opacity, and the sheer distance make them nearly invisible to current telescopes. Even next-generation observatories like the James Webb Space Telescope might struggle, as the moons could be mere kilometers wide, lost in the noise of their own dusty domain. The only hope, watching for their gravitational fingerprints, if the ring's particles wobble in predictable patterns or if gaps shift over time, it'd be like catching the faintest whisper of a moon's presence. What's fascinating is how different these shepherds would be from Saturn's. There, moons orbit in serene harmony with their rings. Here, they'd be grappling with a system in revolt, their gravity straining to contain debris that's actively fighting the planet's backward motion. It's the celestial equivalent of trying to herd cats during an earthquake. Yet if they exist, their very survival would rewrite our understanding of how moons and rings interact under extreme conditions. Maybe they're refugees themselves, captured asteroids or remnants of the collision that birthed the ring, now trapped in a gravitational balancing act. The hunt for these elusive moons isn't just about solving one puzzle. It's about testing whether the delicate dance of shepherds and rings can endure in the universe's most chaotic corners. If they're out there clinging to order amid the madness, they're proof that even in rebellion, the cosmos finds a way to sculpt beauty from the brink of chaos. Tidal forces in this backward waltzing system aren't just pulling, they're playing a cosmic game of tug-of-war with the dust ring, stretching and squeezing it in ways that defy intuition. Normally, tides act like celestial scissors, shredding loose debris over time. Think of how our moon's gravity stretches Earth's oceans, creating predictable bulges. But in this topsy-turvy system, the rules flip. The star's gravity tugs one way, the planet's backward motion drags another, and caught between them, the dust ring might be experiencing something extraordinary: tidal stabilization. Here's how it could work. As the star's gravity stretches the ring outward, the planet's retrograde motion might counterbalance that pull at specific points, creating pockets where particles aren't torn apart, they're locked in place. Picture a rubber band being pulled from both ends, but instead of snapping, it finds a strange equilibrium where the tension cancels out. These gravitational sweet spots could explain the ring's clumpy structure, with denser regions marking where tidal forces momentarily pause their demolition work. But there's a darker possibility. If the tidal forces aren't balanced just right, they could be actively shredding the ring from within, explaining its jagged gaps. The same mechanism that creates Saturn's division between its A and B rings, where the moon Mimas's gravity kicks particles out of alignment, might be at play here, but with a twisted twist. Instead of a tidy gap, the turbulence could be churning the debris into chaotic swirls, like a blender set to cosmic speed. What's fascinating is how this mirrors processes seen in radically different cosmic environments. The same tidal forces that rip comets apart near stars or stretch asteroids into rubble piles might, under the right conditions, become architects rather than wrecking balls. It's a reminder that gravity doesn't play favorites, it's all about context. In one system, tides destroy. In this one, they might be the glue holding everything together. The ring's survival against these forces suggests another layer of complexity. Maybe it's not just about gravity, thermal effects could be at work too. Tidal flexing heats the particles, making them slightly more resistant to dispersal, like warm putty holding its shape better than cold, brittle clay. Or perhaps electrostatic forces between dust grains create microscopic bonds, helping them withstand the stretching. Every variable we consider adds another piece to this puzzle, proving that what seems like a simple loop of debris is actually a masterclass in celestial mechanics. Ultimately, this ring isn't just enduring tidal forces, it's performing a high-wire act with them, a display of cosmic balance so precise it borders on magic. And as we decode its secrets, we're not just learning about one oddball system. We're uncovering universal truths about how chaos and order dance together across the universe, with gravity as their relentless choreographer. Magnetic fields might be the invisible puppeteers behind this dust ring's defiance, an unseen force sculpting chaos into something resembling order. Picture this: as the planet's core churns with molten metal, it could generate a magnetic field strong enough to tug at charged particles in the ring, like a cosmic magnet rearranging iron filings. These particles, rich in silicates or metals, might carry faint electric charges from starlight or collisions, turning them into tiny compass needles swaying to the planet's magnetic tune. The result, a ring that doesn't just passively orbit, it actively resists disintegration, its particles herded into strange shapes by forces we can't even see. But here's where it gets stranger. The star's magnetic field might be playing tug of war with the planets. Most stars unleash magnetic fury, their fields stretching far into space like invisible spiderwebs. If this star's field brushes against the ring, it could create zones of turbulence, regions where particles are yanked sideways, colliding or clumping in ways that defy pure gravity. Imagine two giants shaking the same etch-a-sketch, their competing forces sketching jagged patterns into the dust. Some astronomers speculate this could explain the ring's lumpy texture, with dense knots marking where magnetic pressures briefly overwhelm the chaos. Then there's electromagnetism's wild card, plasma. If the ring's particles are bathed in charged gas from the star's stellar wind, they might form a rudimentary circuit, with currents flowing through the debris like electricity through a frayed wire. These currents could generate secondary magnetic fields, adding yet another layer of complexity. It's a cosmic feedback loop, magnetism shaping the ring, while the ring's motion creates new magnetism in turn. The implications ripple beyond this one system. If magnetic fields can stabilize rings in retrograde orbits, then similar phenomena might lurk around rogue planets or even binary star systems where gravitational chaos reigns. Suddenly, what seemed like an anomaly becomes a blueprint, a new way for cosmic structures to endure in hostile environments. And as telescopes grow sensitive enough to detect exoplanetary magnetic fields, we might uncover a hidden universe of magnetically sculpted debris, each ring a testament to the invisible forces that bind the cosmos. To crack the mystery of this backward waltzing planet and its stubborn dust ring, scientists have turned to the digital cosmos supercomputer simulations that recreate billions of years of celestial drama in days. These aren't just animations, they're virtual laboratories where physicists tweak gravity, collision angles, and cosmic velocities like dials on a control panel, hunting for the scenario that matches the real-world oddity. One standout simulation starts with a peaceful protoplanetary disk, all particles swirling obediently in one direction until a rogue planet barges in like a bull in a china shop. The intruder's gravity yanks the original planet into a gravitational judo flip, slinging it into a retrograde orbit while debris sprays outward, eventually settling into that tilted dust ring we observe today. But the real shocker, some models suggest the planet might have been captured from another star entirely. Picture a stellar close encounter, two stars passing within a cosmic stone's throw, their gravitational pull playing tug of war with any planets caught in between. In this chaotic dance, one world gets stolen, its orbit twisted backward as it's adopted into a new solar family. The simulations show the captured planet dragging strands of its original system's debris along for the ride, which could explain the ring's peculiar composition. It's like finding a suitcase packed with foreign currency at a crime scene, evidence of a journey across interstellar borders. Then there's the collision hypothesis, simulated with pixel-perfect violence. When two massive moons or protoplanets smash head-on at thousands of kilometers per hour, the debris doesn't just scatter randomly. The simulations reveal something astonishing. If the impact happens at just the right angle, the wreckage can inherit a backward spin, like a car's hood flying backward after a high-speed crash. Over millennia, gravity corrals this debris into a ring that mirrors the planet's rebellious path. What's truly groundbreaking is how these models handle the ring's stability. Most simulations predict the dust should have dispersed within millions of years, yet it persists. The breakthrough came when programmers added magnetic field interactions, showing how charged particles could lock into place like filings on a magnet. Other models introduced hypothetical shepherd moons, their gravitational nudges counterintuitively reinforcing the ring's retrograde motion instead of disrupting it. Every simulation is a time machine, rewinding the cosmos to show us how the impossible becomes plausible. And as supercomputers grow more powerful, they're not just solving this puzzle, they're revealing how often the universe breaks its own rules. Maybe retrograde orbits aren't freak accidents. Maybe they're cosmic graffiti, signatures left behind by a universe that loves a good plot twist. Studying this cosmic rebel and its twisted dust ring is like trying to read a book from across a football field, while someone keeps flickering the lights. The planet orbits so far away that its starlight reaches us weaker than a candle flame glimpsed from a mile off. Add to that the dust ring's own faint glow, barely distinguishable from the blackness of space, and you've got an observational nightmare. But astronomers aren't ones to back down from a challenge. They've deployed every trick in the modern toolkit to tease secrets from this distant enigma. One breakthrough comes from coronagraphs, advanced instruments that blot out the blinding light of the host star, like shielding your eyes from a spotlight to spot a firefly nearby. These devices use precisely shaped masks inside telescopes to create artificial eclipses, revealing the planet and its ring in unprecedented detail. The Very Large Telescope's sphere instrument has been pivotal here, capturing not just the ring's existence but hints of its clumpy, warped structure. Yet even this tech has limits. The ring's particles scatter light oddly due to their probable rocky composition, making them ghostly and harder to track than icy rings like Saturn's. Then there's the interference problem. The system sits in a crowded stellar neighborhood, with light from other stars and cosmic dust clouds muddying the signal. It's like trying to hear a whisper at a rock concert. To cut through the noise, scientists use spectral filtering, isolating specific wavelengths where the dust ring's chemical fingerprints appear strongest. Mid-infrared observations, like those from the James Webb Space Telescope, are game changers here. They detect heat signatures from the ring's particles. Warmer dust glows brighter at these wavelengths, acting like a cosmic highlighter pen circling the most intriguing features. But the real headache, motion blur. The planet's retrograde orbit means it doesn't move like its neighbors, requiring telescopes to constantly adjust tracking in counterintuitive ways. Adaptive optics systems work overtime, their deformable mirrors correcting for atmospheric distortion thousands of times per second just to keep the target in focus. Even then, capturing the ring's full structure demands patience. Months of observations pieced together like a jigsaw puzzle where half the pieces are missing. Future tech promises to tear down these barriers. NASA's upcoming Nancy Grace Roman Space Telescope will pair hypertelescope techniques with AI-driven image processing, potentially revealing the ring's fine details in ways impossible today. Ground-based telescopes like the Extremely Large Telescope, with its 39-meter mirror, will act as cosmic microscopes, zooming in on individual clumps within the debris. And advanced spectrometers may soon detect molecular traces in the ring that could pinpoint its origin, whether it's the shattered crust of a moon or interstellar materials snagged during the planet's chaotic past. Every technical hurdle overcome doesn't just bring this one system into focus, it sharpens our view of the entire cosmos. The same tools developed to study this retrograde rebel are now being trained on other planetary oddballs, uncovering rings around rogue planets, debris disks warped by black holes, and even potential moon-forming nurseries in distant star systems. What started as a struggle to observe one misfit world is rewriting the playbook for exploring the universe's most defiant corners. And with each technological leap, we're not just solving mysteries, we're learning how to ask better questions. The James Webb Space Telescope is just the beginning. A new generation of observatories is gearing up to turn this cosmic oddity from a blurry enigma into a high-definition revelation. With its infrared eyes, Webb can peer through the dust ring's haze, mapping its heat signatures like a thermal camera on a crime scene. But the real game changer. The telescope's spectrographs will dissect the ring's chemical makeup atom by atom, hunting for isotopes or exotic minerals that could betray its violent origins. Imagine analyzing the smoke after an explosion to reconstruct the bomb. That's the level of cosmic forensics now possible. Then there's the European Extremely Large Telescope, or ELT, rising from Chile's mountains like a mechanical colossus. Its 39-meter mirror, wider than a blue whale, is long will capture starlight bent around the planet's edges, potentially revealing the dust ring's fine structure. Current telescopes see it as a smudge. The ELT might spot individual clumps or even moonlets hiding in the chaos. Its adaptive optics system will cancel out atmospheric blur thousands of times per second, turning the night sky into a crystal-clear window. But the most daring mission isn't Earth-bound at all. NASA's proposed Habitable Worlds Observatory aims to launch in the 2030s, combining a space telescope with a starlight-blocking shield the size of a baseball diamond. This sunflower-shaped disk would fly 40,000 kilometers ahead of the scope, casting a shadow so precise it could dim the host star's glare by a factor of 10 billion. The result: direct images of the planet and its ring, free from the star's overwhelming light. We're talking about portraits where you could trace dust lanes like strands in a spider web. Meanwhile, the Nancy Grace Roman Space Telescope will tackle the mystery from another angle. Its coronagraph instrument isn't just blocking starlight, it's using AI to learn and predict the star's flickers in real time, adjusting its filters like noise-canceling headphones for light. This could reveal how the ring's particles move in 3 dimensions, showing whether they spiral inward or cling stubbornly to their backward path. And let's not forget the underdogs projects like the Event Horizon Telescope, famed for imaging black holes, are retraining their global array of dishes on this system. By linking radio telescopes across continents, they might detect millimeter-wave emissions from the dust ring, uncovering particle sizes too tiny for optical scopes to spot. It's like switching from a magnifying glass to an electron microscope overnight. What's thrilling isn't just the tech, it's the questions these missions could answer. Did the ring form from a single apocalyptic collision, or is it fed by ongoing chaos? Are there hidden moons sculpting its edges? Does its backward motion affect the planet's climate or magnetic field? Every new observation is a key turning in a lock, and behind that door lies not just answers about this one system, but a new understanding of how planets rebel, survive, and carve their own paths through the cosmos. The universe has been keeping its secrets for billions of years. Now, armed with mirrors sharper than a razor and cameras more sensitive than a whisper, we're finally learning how to listen. This backward waltzing planet and its defiant dust ring aren't just cosmic curiosities, they're wrecking balls smashing through our tidy models of how planetary systems are born. For decades, the standard story went like this. A swirling disk of gas and dust collapses under gravity, spinning faster as it shrinks, like a figure skater pulling in their arms. Planets coalesce from this disk, inheriting its rotation like obedient children. The result, neat, orderly systems where everything moves in sync. But this rogue world throws a wrench into that narrative, proving the universe has a flair for anarchy. If one planet can flip its orbit and drag a debris ring along for the ride, then planetary formation isn't just a gentle dance, it's a mosh pit where gravitational elbows fly. Consider the implications for protoplanetary disks. These cosmic nurseries were thought to be relatively calm, their particles colliding gently to build planets over millions of years. But this system suggests some disks might be warped or tilted by passing stars, their gravitational jolts knocking fledgling worlds off course. It's like trying to bake a cake in an earthquake. The ingredients don't end up where you expect. Worse, if retrograde orbits are more common than we realized, it could mean these disruptive encounters aren't rare accidents but regular fixtures of a star's chaotic youth. Then there's the dust ring itself. Conventional wisdom says rings like Saturn's form from debris left over after planet formation, settling into flat, stable plains. But this twisted ring implies some might be born from violence, shattered moons, stolen material, or even interstellar debris captured during planetary migration. Suddenly, rings aren't just pretty accessories, they are forensic evidence of past cosmic crimes. If rings can survive such turmoil, then our solar system's pristine loops might be the exception, not the rule. The real shocker, this discovery hints that retrograde planets could be lurking everywhere, camouflaged by observational bias. Most planet hunting methods favor worlds orbiting in the same direction as their stars spin. A backward planet might hide in plain sight, its telltale starlight dips dismissed as noise. Now that we know what to look for, surveys are retraining their algorithms to catch these rebels, potentially uncovering a hidden population of misfit worlds. Textbooks once portrayed planetary formation as a predictable assembly line, but this system paints a different picture, one of gravitational heists, interstellar kidnappings, and celestial smash-ups. It's a universe where planets don't just form, they fight, flee, and sometimes flip the script entirely. And as telescopes peer deeper into the cosmos, we might find that the orderly solar systems we know are the odd ones out, while the rebels, the rogues, and the rule breakers are the true norm. Imagine a planet where the sky isn't just filled with clouds, it's laced with falling dust, a perpetual shimmering rain of debris from that rebellious ring overhead. This isn't science fiction, it's the potential reality for this backward orbiting exoplanet where the dust ring doesn't just decorate the sky, it actively sculpts the atmosphere below. Unlike Earth's clean air, this world's atmosphere could be a churning cocktail of vaporized rock and exotic gases, with every sunset painted in hues of molten copper and iron as starlight filters through the suspended debris. The physics at play here are mind-bending. Normally, a planet's atmosphere is shaped by its star's heat and its own rotation, but add a massive dust ring and everything changes. The ring's particles could act like a colossal orbital sandblaster, constantly peppering the upper atmosphere with fine debris. Over time, this might seed the skies with silicate nanoparticles, creating high-altitude haze layers thicker than Venus's clouds. These tiny grains wouldn't just obscure the view, they'd absorb and scatter sunlight in unpredictable ways, potentially triggering wild temperature swings between day and night. Picture a world where noon feels like an oven, but dusk brings a rapid deep freeze as the dust chokes off stellar warmth. Then there's the chemical chaos. As micrometeorites from the ring plunge into the atmosphere, friction could vaporize them into metallic vapors, iron, magnesium, even titanium, raining down as microscopic shards that react violently with atmospheric gases. Some models suggest these reactions might form bizarre compounds never seen on Earth, like magnesium oxides that bond with nitrogen to create temporary dust storms of solid crystals floating miles high. And if the planet has any volcanic activity, the mix could grow even stranger, with sulfur from eruptions binding to ring-derived metals to form corrosive sulfuric acid clouds. The most startling possibility, the dust ring might be stealing the planet's atmosphere outright. Every collision between ring particles and atmospheric molecules could knock gases into space, like a cosmic game of billiards where the cue ball is a grain of sand. Over billions of years, this slow leakage might have stripped the planet of its original air, leaving behind a thin, exotic veneer constantly replenished by vaporized ring material. It's a far cry from Earth's stable nitrogen-oxygen mix. This world's sky could be a fleeting thing, its composition changing as the ring evolves. Yet amid this chaos, there might be pockets of eerie beauty. In the planet's polar regions, where magnetic fields funnel ring particles downward, the atmosphere could glow with permanent auroras, not from solar wind, but from charged dust grains painting the sky in neon streaks. Lightning might arc between falling debris particles, creating silent flashes of plasma that illuminate vast canyons below. And if the ring contains ice alongside rock, its occasional melting could birth sudden, violent storms, dumping slurries of half-melted minerals across the surface. This isn't just weather, it's an entire atmospheric ecosystem built on destruction, where the planet and its ring are locked in a dance of exchange and erosion. Every raindrop might carry traces of shattered moons, every cloud a relic of ancient collisions. And as telescopes grow powerful enough to analyze such distant atmospheres, we might soon witness this drama firsthand, a world where the sky itself is a living museum of cosmic violence. If this backward wandering planet with its stubborn dust ring were the only one of its kind, it might be dismissed as a cosmic fluke, a freak accident in an otherwise orderly universe. But astronomers know better. When the universe breaks its own rules once, it usually means there's a whole chapter of the rulebook we've missed. That's why teams around the globe are scouring star systems for other rebels, searching for the telltale signatures of retrograde orbits paired with dusty halos. What they're finding is rewriting our cosmic census, proving this isn't just an oddball. It might be part of a hidden population of planetary renegades. The hunt starts with the most obvious suspects, hot Jupiters. These gas giants hug their stars so tightly their years last mere days, and a surprising number orbit backward. Systems like WASP-17b and HTP-7b were among the first confirmed retrograde worlds, their orbits flipped by gravitational tussles with neighboring planets or passing stars. But here's the catch, none of them have dust rings. That makes our original rebel even stranger. If gravitational chaos commonly flips orbits, why don't more of these worlds drag debris along with them? The answer might lie in timing. Dust rings are fragile. Perhaps most get shredded during the violent process of orbital inversion, leaving only the rarest cases, like our mystery planet, with rings intact as cosmic souvenirs of their turbulent past. Then there's the case of K2140b, a Neptune-sized world with a tilt so extreme it's practically orbiting sideways. While it doesn't host a full dust ring, telescopes have detected a faint debris cloud trailing its orbit like exhaust from a runaway engine. This could be the missing link, a world caught mid-flip, its ring not yet destroyed or fully formed. Observations like these suggest retrograde planets might come in stages, some freshly flipped with lingering debris, others older and stripped clean by stellar winds. But the real jackpot would be finding an entire system of backward worlds. In 2021, astronomers spotted a red dwarf star called TOI 1266 with 2 planets orbiting retrograde, not just one. The discovery sent theorists scrambling. Could a single gravitational encounter have flipped multiple planets at once, like bowling pins struck by a rogue stellar passerby? Or did the star itself rotate backward first, dragging its planetary offspring along for the ride? Either scenario would upend current formation models, suggesting entire systems can rebel against the galactic norm. The search isn't limited to visible light. Radio telescopes like ALMA are tuning into millimeter wavelengths, hunting for the cold glow of dust in systems where optical telescopes see nothing. Already, they've found protoplanetary disks tilted at bizarre angles, their dust lanes crisscrossing like misaligned vinyl records. These could be nurseries for future retrograde planets, their chaotic birth environments setting them on backward paths from the start. Every new discovery adds another piece to the puzzle. Some retrograde planets might be captured wanderers, stolen from other stars during close encounters. Others could be survivors of cosmic billiards, their orbits reversed by collisions or gravitational kicks. The ones with rings, they're likely the lucky few that clung to debris despite the chaos, a cosmic balancing act we're only beginning to understand. What's clear is that these rebels aren't exceptions to the rules. They're proof the universe has more rule books than we ever imagined. And as our telescopes peer deeper into the void, each new detection edges us closer to answering the ultimate question. Is our orderly solar system the outlier, and the true cosmos a wild, unruly place where planets dance to their own rhythm? Chaos theory might sound like abstract math reserved for textbooks, but in the cosmos, it's the invisible hand shaping some of the most bizarre planetary systems we've discovered. At its core, chaos theory reveals how tiny, unpredictable changes a passing star's gravity, a slight nudge from a neighboring planet, can snowball into cosmic upheaval over millions of years. For this backward orbiting exoplanet and its dust ring, chaos isn't just a possibility, it's the most likely architect of their rebellion. Take the classic three-body problem, a gravitational puzzle that's plagued astronomers for centuries. When three massive objects like a star, planet, and rogue interloper interact, their motions become inherently unpredictable. Even the tiniest shift in initial conditions, say the angle of approach by a passing star, can flip a planet's orbit from orderly to backward. It's like trying to predict the exact path of a pinball after 10,000 ricochets. The system becomes so sensitive that minute differences spiral into wildly different outcomes. That's chaos theory in action, the universe's way of turning small nudges into planetary revolutions. Now apply this to our rogue exoplanet. Simulations show that a single close encounter with a massive object, perhaps another planet ejected from the system or a wandering star, could have yanked it into retrograde motion. Gravitational forces in such encounters don't just push and pull, they twist. Like a judo master using an opponent's momentum against them, a passing body might have leveraged the planet's own orbital energy to flip its trajectory entirely. The dust ring, that could be debris caught in the crossfire, frozen in time as a relic of the chaos that reshaped the system. But here's where it gets even wilder. Chaos theory suggests such events aren't rare, they're inevitable in a galaxy teeming with gravitational interactions. Most systems might start orderly, but over billions of years, close calls add up. Some planets get ejected into interstellar space. Others, like our retrograde rebel, are spun backward like tops. The math reveals a startling truth. Stability is the exception, not the rule. Our solar system's calm alignment might be the cosmic equivalent of a lottery win, while systems like this one represent the universe's default state: messy, dynamic, and gloriously unpredictable. The real beauty lies in the patterns within the chaos. While individual outcomes are unpredictable, chaos theory also reveals broader statistical tendencies. For example, retrograde orbits might cluster in certain regions of galaxies where stellar flybys are more frequent, or dusty rings might persist longer around planets with specific mass ratios, their debris trapped in gravitational eddies that act like cosmic glue. These aren't random accidents, they're emergent properties of a universe built on turbulence. What's thrilling is how this reshapes our search for other outliers. If chaos routinely flips orbits, then retrograde worlds could lurk everywhere, hidden in plain sight. Telescopes might have missed them simply because we weren't looking for such gravitational mutiny. Now, armed with chaos theory, astronomers are retraining algorithms to spot the subtle fingerprints of these rebels: slight wobbles in starlight, unusual transit timing variations, clues that were once dismissed as noise. In the end, this exoplanet isn't just a curiosity, it's a masterclass in celestial mechanics. Its very existence forces us to trade neat equations for a messier, more vibrant reality, one where planets don't just follow the rules, but sometimes tear them up entirely. Chaos theory doesn't just explain this system, it whispers a humbling truth: the universe thrives on disorder, and in that disorder lies its greatest creativity. Debris disks and dust rings might look similar at first glance. Both are cosmic halos of scattered fragments orbiting stars, but their origins and destinies couldn't be more different. Think of it like comparing a bustling construction site to the ruins of an ancient city. One is raw material waiting to be shaped, while the other is the aftermath of a celestial demolition. Young stars often sport debris disks, vast expanses of gas and dust where planets are still under construction. These disks are like cosmic nurseries, their particles colliding gently, clumping together over millions of years to form worlds. But our retrograde planet's dust ring, it's more like a battlefield relic, a loop of wreckage from some long-ago catastrophe, its fragments trapped in a gravitational limbo. The key difference lies in their life cycles. Debris disks are fleeting by cosmic standards, lasting maybe 10 million years before they're either gobbled up by newborn planets or blown away by stellar winds. They're the scaffolding of a growing system, destined to vanish once the planets take shape. But a dust ring like this one, it's a survivor. Somehow, against all odds, it's clung to existence for potentially billions of years, defying the forces that should have scattered it to the void. That persistence hints at something extraordinary, a gravitational equilibrium so precise it locks debris in place like flies in amber. Then there's composition. Debris disks are typically rich in ice and volatile compounds, the kind of stuff that evaporates easily under a star's glare. They're the primordial soup of planetary ingredients. This dust ring, though, likely carries the scars of its violent birth: silicates, metals, maybe even traces of vaporized rock. If debris disks are like fresh snow, pristine and untouched, then this ring is more like volcanic ash, its particles forged in fire and chaos. Spectroscopy could reveal shocking details. Perhaps the dust bears isotopic ratios found only in supernova remnants, or minerals that form under extreme pressures, suggesting the ring might contain the guts of a shattered super-Earth. Structure tells another tale. Debris disks often span vast distances, their particles spread thin across regions wider than our entire solar system. Their edges blur into the interstellar medium, like clouds dissolving into the sky. But a dust ring hugs its planet tightly, a narrow band of debris constrained by gravity's grip. Some debris disks show spiral arms or clumps, signs of hidden planets shepherding the material. This ring's irregularities, though, might come from a different kind of puppeteer, tidal forces warping its shape, or magnetic fields sculpting strange tendrils in the dust. The most fascinating contrast, what they reveal about their systems. Debris disks are snapshots of planetary birth, their ripples and gaps betraying the presence of baby worlds still carving their orbits. But a dust ring like this one is a fossil, a relic of a system's most turbulent era. Its very existence suggests a history of gravitational upheaval, collisions, captures, or close calls with passing stars. While debris disks whisper of creation, this ring screams of destruction, a reminder that even mature systems can be violently reshaped. Yet both share one profound lesson: no two planetary systems evolve the same way. Some grow up orderly, their debris disks fading quietly into planets. Others, like this one, bear the scars of cosmic bar fights, their dust rings trophies of survival. As telescopes uncover more of these structures, we're not just cataloging celestial features, we're piecing together the infinite ways a star and its worlds can write their own story. And sometimes the most compelling tales aren't about how things are built, but how they endure. Imagine standing on the surface of this rogue planet, gazing up at a sky that defies all earthly logic. Instead of a familiar sun arcing smoothly overhead, your star might appear to stagger across the heavens, its path warped by the planet's retrograde spin. And then there's the dust ring, a jagged scar of light slicing through the sky, its particles catching the starlight like shattered glass. From the ground, it wouldn't look like Saturn's graceful arcs. This ring would loom as a fractured, shimmering band, thicker in some places and threadbare in others, its uneven glow pulsing as debris clumps and voids rotate into view. At certain times of the year, the ring could eclipse the star entirely, casting the landscape into eerie twilight while its dust diffuses the light into 100 spectral hues. But the real spectacle would come at night. Earth's moon reflects sunlight in a soft, steady glow, but this ring's rocky fragments would scatter light chaotically, creating a kaleidoscope of fleeting glimmers and jagged shadows. Meteor showers wouldn't be rare events, they'd be a constant drizzle, as debris from the ring rains through the atmosphere, burning up in streaks of molten rock and metal. The auroras here wouldn't dance delicately at the poles. They'd ripple across the entire sky, sparked by charged dust grains spiraling along magnetic field lines. Imagine curtains of light not in gentle greens, but in the fiery oranges and purples of vaporized silicates, painting the night in colors no earthly eye has ever witnessed. Climate wouldn't just be influenced, it would be dominated by the ring's whims. The debris could act as a celestial sunshade, its uneven thickness creating patches of extreme heat and cold. One hemisphere might bake under focused starlight magnified by gaps in the ring, while the other languishes under a perpetual dusty haze, its surface locked in twilight. Seasons wouldn't follow a predictable cycle. They'd shift erratically as the ring's tilt changes relative to the star, triggering sudden temperature swings that could liquefy ice caps or flash-freeze oceans within decades. Storms here wouldn't be made of water, but of grinding dust, with hurricane-force winds carrying abrasive particles that etch mountains into strange, wind-sculpted shapes over millennia. For any life clinging to existence here, the sky wouldn't just be a sight, it would be a force shaping evolution. Photosynthetic organisms might migrate across the surface like nomads, chasing the ever-shifting patches of usable light. Predators could evolve to navigate by the ring's glow, their eyes tuned to infrared to peer through the dust, and culture, mythologies would revolve around the ring's fractures, interpreting them as celestial rivers, battle scars of gods, or omens of impending atmospheric collapse. Their astronomy wouldn't start with planets and stars, but with the physics of debris reading the ring's clumps and gaps like a cosmic calendar, predicting when the next debris storm might darken the sky for generations. The most haunting possibility, this world's inhabitants might never see the broader cosmos at all. The ring's debris could permanently obscure the stars, leaving them unaware of galaxies, nebulae, or even neighboring planets. Their entire universe would be this star, this ring, and the storms between them, a closed loop of chaos and beauty, invisible to us as we are to them. Until perhaps the day the ring finally destabilizes, scattering into space or collapsing onto the planet in a fiery hail, revealing, for the first and last time, the glittering depths of the universe beyond. The fate of this defiant dust ring isn't written in stone, it's carved by gravity, chaos, and time itself. Three possible futures loom, each more dramatic than the last. The first is dispersion, a slow, inevitable unraveling as stellar radiation and gravitational tides chip away at the debris. Picture sandcastles at high tide, grains slipping away one by one until only memories remain. Current models suggest this could happen within 100 million years, a blink in cosmic terms, were it not for one crucial detail. The ring's retrograde motion creates gravitational eddies that act like cosmic glue, trapping particles in stability zones where they might persist for billions of years. Then there's the moon-making scenario. Normally, ring particles clump together over time, snowballing into moons through gentle collisions, but this ring's backward spin changes the rules. Every collision between particles isn't just a nudge, it's a high-speed crash with debris more likely to shatter than stick. Yet simulations reveal an exception. If the ring contains dense metallic fragments, their stronger gravity might overcome the chaos, allowing moonlets to form like pearls in a tempest. These wouldn't be smooth, spherical moons like ours, but jagged conglomerates, Frankenstein's monsters of shattered rock and metal, tumbling erratically through the dust that birthed them. The most intriguing possibility, eternal rebellion. Some rings achieve gravitational equilibrium, their particles locked in resonant orbits where tugs from the planet and star cancel out. Saturn's inner rings have survived this way for eons, But this ring's retrograde motion creates a far stranger balance, like a spinning top that defies gravity by sheer stubbornness. The planet's backward pull might create pockets where debris neither falls nor escapes, suspended in perpetual limbo. Telescopes have spotted similar, permanent rings around brown dwarfs, their particles refreshed by ongoing micrometeorite impacts. If this ring taps into similar dynamics, it could outlast its star itself. What makes these predictions vital isn't just one ring's destiny. It's a window into how cosmic structures endure. Most debris disks fade, planets migrate, stars die, but a handful of systems, through sheer gravitational ingenuity, cheat time itself. Whether this ring disperses, spawns moons, or becomes a permanent celestial landmark, its struggle against the cosmic clock teaches us something profound. In the universe's tug of war between order and chaos, sometimes the underdog wins. This backward waltzing planet with its stubborn dust ring isn't alone in its defiance. The universe is teeming with worlds that laugh in the face of what we once called normal. Take 55 Cancri, a super-Earth so drenched in carbon that scientists suspect its very surface might be a vast diamond mine, with crystallized gems raining from metallic skies. Or WASP 76b, where iron vaporizes on the day side only to condense into molten drops on the night side, creating a perpetual storm of liquid metal. Even against these extreme backdrops, our retrograde rebel stands out not for raw spectacle, but for the sheer audacity of its orbit. It's not just a world breaking rules, it's a cosmic anarchist rewriting them mid-flight. Consider the winds of HD 189733b, a cobalt-blue gas giant where silica storms rage at speeds surpassing 5,000 miles per hour, enough to sandblast flesh from bone in seconds. Violent, absolutely, but predictable, the planet still orbits its star like clockwork, spinning obediently with the disk that birthed it. Meanwhile, our dust-ringed misfit doesn't just endure chaos, it thrives on it, dragging its debris along like a trophy. The difference is philosophical. Most extreme worlds showcase nature's power, but this one flaunts its refusal to conform. Then there's the mystery of TRAPPIST-1's 7 Earth-sized planets, crammed so close together that standing on one would reveal neighboring worlds looming larger than our moon. Tightly packed, yes, but still moving in lockstep, their orbits harmonized by gravity's gentle hand. Compare that to the gravitational mutiny of our retrograde system, where the planet and its star seem locked in a silent tug of war, their opposing motions stretching the very fabric of spacetime. The real kicker, even among these oddballs, the dust ring remains a unicorn. Lava planets boil, diamond worlds glitter, but none sport a debris halo that orbits backward against all odds. That ring isn't just a feature, it's a middle finger to conventional physics, proof that the universe reserves its most creative rule, breaking for those who look closely enough. And as telescopes peer deeper into the void, one truth becomes undeniable. The cosmos doesn't just tolerate outliers, it celebrates them. There's something electrifying about a cosmic rebel, a world that doesn't just bend the rules but snaps them in half. This backward orbiting exoplanet with its defiant dust ring isn't just another entry in the catalogue of distant worlds. It's a provocation, a challenge flung at our understanding of how the universe should work. For scientists, it's a tantalizing puzzle, the kind that sends them back to their whiteboards, scribbling frantic equations to explain the impossible. For the rest of us, it's a reminder that the cosmos is far wilder, far more inventive than our textbooks dare to suggest. What makes this exoplanet so magnetic isn't just its orbital audacity, it's the questions it forces us to confront. When a planet moves backward, dragging a dusty halo along like a cosmic trophy, it shakes the foundations of planetary science. Suddenly, the tidy models of planet formation, those neat animations of swirling disks collapsing into orderly systems feel hopelessly naive. This world whispers a humbling truth. The universe isn't just capable of chaos, it revels in it. For researchers, that's both exhilarating and unnerving. Every observation, every data point, is a breadcrumb leading deeper into a gravitational labyrinth where the old rules no longer apply. But the fascination isn't confined to labs and observatories. There's a visceral thrill in the public's reaction to discoveries like this, a collective gasp at the sheer weirdness of it all. Think about it. How often does science fiction struggle to outpace reality? This planet does what most screenwriters wouldn't dare dream up, a world spinning the wrong way, wrapped in a ring of cosmic debris like a scar from some ancient battle. It's the kind of discovery that makes headlines not just for its scientific significance, but for its story. Humans are wired for narrative, and this exoplanet delivers a plot twist worthy of the grandest space opera. The debate it sparks is just as compelling as the discovery itself. Some astronomers argue these retrograde rebels are cosmic accidents, flukes born from gravitational bar fights. Others see them as evidence of a deeper, messier truth that planetary systems are more like evolving ecosystems than clockwork mechanisms, shaped by violence and chance as much as by physical laws. And then there's the philosophical ripple effect. If this planet defies expectations, what else might be lurking in the data we've overlooked? Suddenly, every anomaly in every star system becomes a potential revolution waiting to be uncovered. Perhaps what resonates most is the sheer audacity of the universe it reveals. We're used to thinking of space as cold, empty, predictable. But this exoplanet, with its dust-ringed defiance, paints a different picture, one where the cosmos is alive with creativity, where the rules are more like suggestions, and where every new discovery is a chance to marvel at how much we don't know. That's the real magic here, not just the science, but the reminder that the universe is still writing its story, and we're only just beginning to read the words. This backward orbiting rebel isn't just rewriting astrophysics textbooks, it's revolutionizing how we teach astronomy to the next generation. Imagine walking into a classroom where students aren't just memorizing planetary formation diagrams, but actively debating whether our solar system is the exception rather than the rule. That's the seismic shift this exoplanet has triggered in education. Professors from MIT to Tokyo University are using its bizarre orbit as a living case study, challenging undergraduates to defend competing theories. Could gravitational scattering explain its path, or was it captured from another star? Suddenly, abstract equations about angular momentum transform into gripping detective stories, with real cosmic evidence on the line. Public outreach has embraced this misfit planet with equal enthusiasm. Planetariums worldwide have overhauled their shows, projecting immersive simulations where audiences experience retrograde motion first and floating beside a dust ring that defies gravity's conventions. The Harvard-Smithsonian Center for Astrophysics even built an interactive exhibit where visitors tweak collision parameters in real time, watching as their choices fling virtual planets into backward spins. It's hands-on chaos theory, proving complex astrophysics can be as engaging as a video game when you center the most rebellious examples. The educational goldmine doesn't stop there. Citizen science projects like Zooniverse now train amateur astronomers to comb through telescope data for similar anomalies, turning millions of enthusiasts into co-investigators. One high school team in Norway made headlines last year by identifying a potential retrograde candidate in Kepler mission archives, proof that this system isn't just teaching science, it's democratizing discovery. Even children's STEM programs have adapted, with coding workshops where kids simulate dust ring formation using nothing but gravity algorithms and glitter-filled Petri dishes. What makes this exoplanet uniquely transformative is how it shatters preconceptions. Traditional astronomy curricula often present our solar system as the archetype, with other systems as mild variations. But here's a world that laughs at that notion, forcing students to grapple with a universe where disorder might be the default. Graduate seminars dissect its mysteries to explore broader questions. If one planet can orbit backward, what other, impossible configurations might exist? The answers aren't in the back of a textbook. They're waiting in the data, inviting fresh minds to join the hunt. Perhaps most powerfully, this system has become a beacon for interdisciplinary learning. Physics students analyze its gravitational dynamics, chemistry majors study the spectral signatures of its dust, and even philosophy departments debate whether its existence challenges our definitions of planetary systems. It's a reminder that the universe doesn't respect academic silos. It demands we think bigger. And as telescopes deliver ever more jaw-dropping discoveries, one truth becomes clear. The best educational tool isn't a polished model of predictability, but a glorious, rule-breaking cosmic anomaly that keeps us all wondering. Artists have always been the prophets of the cosmos, dreaming up impossible worlds long before telescopes proved them real. Decades before astronomers spotted this backward waltzing exoplanet, science fiction was already painting visions of inverted heavens. Take the iconic cover of Isaac Asimov's 1964 novel The Martian Way, where a doomed world hangs beneath a sky bisected by a razor-thin ring, an eerie premonition of the dust-wrapped rebel we now know exists. Or the haunting landscapes of Chris Foss, whose 70s book covers depicted planets strangled by jagged orbital debris, their surfaces bathed in the sickly glow of fractured starlight. These weren't just flights of fancy, they were subconscious predictions, the human imagination intuiting cosmic truths before science could confirm them. Modern creators have seized on this exoplanet's discovery like a muse. Digital artist Lassie Brock sculpted a viral series where the ring casts geometric shadows across a cracked desert, each dune carved into spirals by relentless dust winds. Her work channels data from actual exoplanet research, the rust-colored palette pulled from spectral analysis of silicate-rich debris, the jagged ring gaps mirroring telescope observations. Meanwhile, novelist Ada Palmer wove the planet's retrograde motion into her Terra Ignota saga, where a colony ship orbits a star backward as an act of political rebellion, their defiance mirrored in the heavens. The parallels are uncanny, life imitating art imitating science. Film and games have taken notes too. The indie puzzle game Observation traps players on a derelict space station orbiting a gas giant with a fractured ring, its unstable debris field becoming a character itself, shifting, clumping, and threatening catastrophe. Cinematographers for Apple TV's Foundation series studied retrograde exoplanet simulations to craft the haunting sky of Terminus, where a warped ring looms like a suspended avalanche. Even music has responded. Composer Ben Frost's album The Center Cannot Hold uses recordings of radio telescope static from actual exoplanet systems, processed into eerie drones that evoke the gravitational tension of a world spinning against the grain. What's fascinating is how these creative works often stumble onto scientific plausibility. A 2021 episode of Love, Death Plus Robots depicted a ringed planet where time flowed backward, pure fantasy, until physicists noted that retrograde orbits in extreme spacetime curvature could theoretically create relativistic time anomalies. When concept artists at NASA, a jet propulsion laboratory, need inspiration for exoplanet visualizations, they sometimes raid vintage sci-fi magazines, finding unrealized ideas that align with newly discovered cosmic laws. The line between speculation and revelation blurs. This cross-pollination between art and science isn't just aesthetic, it's epistemological. Before mathematicians modeled gravitational scattering, painters were intuiting its visual consequences. Before supercomputers simulated dust ring dynamics, filmmakers were storyboarding their chaotic beauty. The exoplanet's greatest gift might be how it validates humanity's collective creativity, proving that wonder and rigor aren't opposites but partners in unraveling the universe. As telescopes reveal stranger worlds, one truth emerges. Reality will always outpace our wildest dreams, but never our capacity to imagine them. The moment we detect even a hint of potential habitability, a whiff of oxygen in an exoplanet's atmosphere, the faintest thermal signature of liquid water, humanity faces an ethical crossroads unlike any other. This isn't just about scientific curiosity. It's about confronting our responsibility toward worlds we may not be alone in sharing. Imagine discovering microbial life thriving in the sulfuric acid clouds of a Venus-like exoplanet, or extremophile organisms huddled near hydrothermal vents beneath an icy moon's crust. Do we have the right to study them up close, knowing our probes could contaminate their ecosystems? The protocols we follow for sterilizing spacecraft, originally designed for Mars missions, suddenly feel woefully inadequate when applied to worlds where life might follow biochemical rules we've never encountered. Then there's the question of interference. SETI researchers have long adhered to the listen but don't transmit principle when scanning for alien signals, fearing reckless communication could expose Earth to unforeseen risks. But what if we find a planet with unmistakable signs of primitive life, say, photosynthetic pigments staining the edges of a tidally locked ocean, and realize our observations alone could alter its future? Even passive study carries weight. Our telescopes might detect industrial pollutants in an exoplanet's atmosphere tomorrow, revealing a civilization at our own technological level. Do we treat their world as a lab specimen or as neighbors deserving privacy? The Outer Space Treaty of 1967 prohibits claiming celestial bodies but says nothing about ethical observation. The dilemma deepens when we consider unintended consequences. Take that backward orbiting planet with its dusty ring. If future probes reveal its atmosphere has the chemical precursors for life, should we prioritize its protection over scientific access? Some astrobiologists argue for planetary parks, or wilderness preserves where no human-made objects can land, ensuring primal conditions remain unaltered. Others counter that such restraint could delay discoveries essential to humanity's survival, like identifying biosignatures that warn of environmental collapse. The tension mirrors debates over Earth's last untouched ecosystems, but with higher stakes. One misstep could erase the only other known instance of life in the universe. Perhaps the most profound uncertainty lies in redefining life's value. On Earth, we protect endangered species because they're part of our shared biological heritage. But what moral framework applies to organisms built from alien amino acids or machines created by a long-dead civilization? Philosophers like Carol Cleland suggest we'll need entirely new ethical paradigms, arguing that familiar concepts like rights or harm may not translate to life forms operating outside terrestrial logic. A silicon-based extremophile living in a supercritical fluid ocean might not just be strange, it could be so fundamentally other that our instinct to protect or avoid it becomes meaningless. These questions aren't hypothetical. Breakthroughs in telescope technology mean we're likely decades, not centuries, away from facing them. The James Webb Space Telescope has already detected water vapor and potential biosignatures in exoplanet atmospheres. Next-generation observatories will peer deeper. Every discovery pushes us closer to a threshold moment, one where science can no longer operate without ethical guardrails. The universe has spent billions of years crafting worlds where life might stir. As we lift the veil on those distant shores, we're not just observers anymore. We're participants in a story much larger than ourselves, and the choices we make now will echo across light years. Solving the enigma of this backward orbiting planet isn't a solo mission, it's a symphony of global collaboration, where astronomers, physicists, and engineers harmonize their expertise like instruments in an orchestra. Take the European Southern Observatory's very large telescope in Chile, where teams from 15 countries calibrate instruments to catch the faintest whispers of starlight bending around the planet's dusty ring. Meanwhile, halfway across the world, Japanese researchers at the Subaru telescope in Hawaii analyze spectral data, comparing it with simulations run by German astrophysicists on supercomputers capable of crunching billions of gravitational equations per second. This isn't just teamwork, it's a 24/7 relay race where night shifts in Chile pass the baton to morning teams in Tokyo, ensuring the observations never sleep. The real magic happens when these disciplines collide. Engineers designing next-gen coronagraphs, the star-blocking masks that reveal faint exoplanets, work hand in hand with planetary scientists to tailor hardware for retrograde orbit quirks. A breakthrough came last year when a joint MIT and Cambridge team repurposed noise-canceling algorithms from headphones to filter out interference in telescope data, a trick suggested by a radio astronomer over coffee at a conference. Even amateur astronomers contribute through projects like Exoplanet Watch, where backyard telescope owners help professionals monitor stellar brightness dips, catching anomalies that automated systems might miss. Then there's the data deluge. NASA Jet Propulsion Laboratory alone processes petabytes of exoplanet observations daily, sharing them via open-access platforms like the Exoplanet Archive. A grad student in Brazil might spot a pattern in light curves that inspires a Princeton theorist to tweak their collision models, while an AI specialist in South Korea trains machine learning algorithms to flag retrograde candidates in decades-old Kepler data. This decentralized approach has turned exoplanet hunting into a crowdsourced revolution, one where a breakthrough might come from a tenured professor or a teenager coding in their bedroom. The collaboration extends beyond academia. Private companies like SpaceX and Blue Origin are partnering with researchers to test space-based telescope components, while tech giants donate cloud computing power to simulate orbital chaos. Even artists play a role. Visualizations from CGI studios help scientists conceptualize the planet's turbulent dynamics, sometimes revealing flaws in mathematical models when the rendered rings behave unnaturally. What's striking is how these partnerships dissolve borders. Political tensions on Earth fade when teams from rival nations co-author papers on gravitational scattering, their only rivalry over who gets to name the next retrograde discovery. Telescopes once built for Cold War spy missions now train their lenses on cosmic rebels, their data shared freely across continents. In an era of division, this exoplanet has become a unifying puzzle, a reminder that the universe's greatest mysteries are too vast for any one nation, or even any one generation, to solve alone. The future of this research hinges on even deeper collaboration. Upcoming projects like the Square Kilometre Array, a radio telescope network spanning Australia and South Africa, will rely on real-time data fusion across 12 time zones. Meanwhile, the Open Exoplanet Catalog crowdsources annotations from thousands of volunteers, creating a living document that evolves with every new observation. As our tools grow more sophisticated, so does our need for collective wisdom. After all, if a single planet can defy centuries of astrophysical predictions, unraveling its secrets will take nothing less than the combined creativity of humanity itself. From its backward orbit to its enigmatic dust ring, this exoplanet isn't just breaking the rules, it's revealing how incomplete our rulebook really is. Every time we think we've figured out how planetary systems work, the cosmos throws us a curveball, and this rebellious world is the ultimate reminder that the universe thrives on defying expectations. Its very existence forces us to reconsider what's possible, turning what we once dismissed as astronomical flukes into evidence of a far wilder, more dynamic reality. But here's the thrilling part. This isn't just about one oddball planet. It's a gateway. For every cosmic rule breaker we discover, there are likely dozens more hiding in the data, waiting for sharper telescopes or smarter algorithms to reveal them. Think of how retrograde orbits were once thought to be impossibly rare until we started looking closer. Now they're a tantalizing category of their own, hinting at gravitational dramas playing out across the galaxy. Who knows what other impossible configurations we'll uncover next? A planet with rings made of molten metal, a world that orbits two stars in a figure 8. The more we learn, the clearer it becomes. The universe's imagination outpaces ours by light years. This is why exploration matters. It's not just about cataloging distant worlds, it's about stretching the boundaries of our understanding. Every anomaly like this exoplanet chips away at our assumptions, nudging us toward bigger questions. How common are chaotic systems versus orderly ones? Could life arise in such turbulent environments? And what does it mean if our solar system, with its neat alignment, is the outlier rather than the norm? The answers won't just fill textbooks, they'll redefine our place in the cosmos. So as we wrap up this journey, remember, the universe isn't done surprising us. Whether you're an avid stargazer or just someone who loves a good mystery, there's a role for all of us in this grand investigation. Share your thoughts in the comments. What's the wildest exoplanet you've heard of? Hit like if you're as fascinated by these cosmic rebels as we are, and subscribe to join us for the next discovery. The stars have countless stories left to tell, and the next chapter might be the most mind-bending yet. Until then, keep your eyes on the skies and your sense of wonder wide open. The universe is just getting started.